Welcome to video 12.5 in our first Principles of Astrophotography series. In this video, we discuss reducers and Barlows, which can improve the framing of your images.
This video is based on section 12.5 of our first Principles of Astrophotography book, which is linked in the description below. I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 134, reducers and Barlows. Focal reducers decrease the focal length and increase the field of view.
Let's stop right there. Decrease the focal length, increase the field of view. So let's look at this EdgeHD 8-inch native. It has an aperture of 203 millimeters, has a focal length of 2032 millimeters. So to find the focal ratio, you take the focal length divided by the aperture, and that's 2032 divided by 203, which gives a focal ratio of 10.
Nice.
When you pair that with an ASI2600 camera that has 3.76 micron pixels, fairly small but not as small as you get a field of view of 0.7 by 0.4 degrees. So suppose you plop a reducer in front of that, which you can buy from Celestron, a 0.7 times reducer. What that does, it doesn't change the aperture because you're not stopping it down or anything like that. All you do with that reducer is to reduce the focal length by a factor of 0.7. So 70% of 2032 is 1422. You've reduced the focal length, and that's why you call them reducers. You've also reduced the focal ratio, because the focal ratio is that number divided by this number. And so you reduce the focal ratio down to 7. Now, what you've done is you've reduced the focal length, which reduces the magnification of the telescope and has increased the field of view. Instead of 0.7 degrees by 0.4 degrees, up to 0.9 by 0.6. Focal length goes down, field of view goes up.
Reducers kind of boggle my mind. I feel like with the telescope that's this big and it covers that much sky, you can't get more.
But you can.
But you can.
But you can.
Yeah.
All right, let's finish the concept.
All right, Barlow lenses are the opposite. They increase the focal length and decrease the field of view.
All right, so let's take this example here. The same telescope natively, but paired with a different camera, the ASI585, which a lot of people use to do planetary imaging. Doesn't have as many pixels and doesn't have as wide a field of view, but the pixels are smaller. So the pixels are 2.9 microns in size, smaller pixels. The number of pixels is smaller, and it gives us smaller field of view, which is great for imaging planets or small objects like planetary nebulae, some planetary nebulae. So what happens if you slap a Barlow on there? A lot of planetary imagers use Barlows so they can approach that diffraction limited resolution of this scope. And we talk about that in our Lucky Imaging video. That's us on video 13.2. So what you do with a Barlow is you increase the focal length, and in this case you double it. So you take 2,000 and you make it 4,000, double the focal length. What have you done to the focal ratio? Well, now we got 4,064 divided by 203. Again, you haven't changed the aperture, and you end up with a focal ratio of 20. And then still paired with this ASI585 camera, the same pixels and the same pixel size, same number of pixels, you've reduced the field of view by a factor of 2. Instead of 0.2 degrees vertically, you have 0.1. Instead of 0.3 degrees horizontally, you divide that by 2 to get 0.15, which rounds up to 0.2. That's the way we've done that calculation.
Yeah. Yeah.
So reducers and Barlows are a great way if you have an object that's a little bit bigger than the field of view that's offered by your native telescope, then use a reducer, and then it gives you a bigger field of view and you can shoot that object. Or if you have one that's really small in your native field of view and you want to get more detail, plop a Barlow on there.
Nice. Barlows.
Barlows. Yep. Thanks for watching.
And we'll see you next time.